Hi, this is Group Function as a Service. This is our last presentation for Boston University Cloud Computing course. Our mentor is Tommy and Lam. Our instructor is Professor Orin Krieger. Okay, so today our presentation, there will be 5 parts. The first one is the introduction, and the second one we will talk about OpenWhisk, and then we will talk about our application, and then we will introduce our benchmark, and then it's the semester review. Okay, so firstly, I will give you a short introduction for our project. So actually, I want to introduce our project by using 3 simple questions. So first one is what we are using, and the second one is what's our goal, and the third one is what we've done. Okay, so for the first question, what we are using, actually we are using a really new technique with the name of which is function as a service. Function as a service is a category of cloud computing service. It allows customers to develop application without the complexity of maintaining the infrastructure. Customers just need to define functions and corresponding trigger method. Then cloud provider can automatically trigger those functions. Actually, there are a lot of advantages for function as a service. First, it's very easy to scale up. Secondly, you can pay as you go. And the third one is that you don't need to configure the cloud, and the cloud provider will help you do that. Actually, there are a lot of famous function as a service. For example, the AWS Lambda and Google Cloud Functions. Okay, so next we will introduce is OpenWhisk. What is OpenWhisk? OpenWhisk is an open source distributed serverless platform, and we will research function as a service based on OpenWhisk platform. Okay, let's talk about our second question. What's our goal? Actually, our goal is pretty simple. We just want to test the performance of function as a service, this technique, and OpenWhisk, this platform, in real application. Okay, so what we've done, actually there are 2 parts. So firstly, we build a real app, which is a taxi application, and then we build a benchmark for monitoring the performance of our application and also the platform and the technique. Okay, so firstly, we build the application inside of the OpenWhisk, and then we deploy the OpenWhisk and our application in the Google Cloud platform, and then we build a front-end visualization platform and a benchmark matrix monitoring system.
Okay, so here I will give a simple introduction of the OpenWhisk deployment. The reason why we choose OpenWhisk is that it's different from some other function as service platforms. The OpenWhisk is an open source project. It's easier to understand the different components of this platform, and also OpenWhisk provides a powerful metric support, which enable us to analyze the whole systems. While also we are deploying this whole OpenWhisk platform on the Kubernetes clusters. This is because deploying OpenWhisk over the Kubernetes can leverage the capabilities provided by Kubernetes to better control and manage OpenWhisk containers, which can result in a stable OpenWhisk runtime. So we first deploy the OpenWhisk locally on Minikube, which is a local single-node Kubernetes clusters. Then we deploy the OpenWhisk over Google Cloud Kubernetes engine.
Then we'll talk about our application. We'll introduce how we build our application step by step, from system architecture to database choice, and then backend, and finally frontend. Here is a brief introduction of our system architecture. We made a driver-passenger application. The backend part receives requests from users, and it will firstly synchronize the user's information. Then, for each driver, it can also search potential passengers in the nearby area. In addition, for all of our users, we also build a website to show their real-time locations. That is our front-end work. We also did some analysis work to evaluate the performance for not only OpenWhisk but also Google Cloud Platform.
Okay, so now let's talk about the database selection. Actually, it's a really important part of our project because we have a really high requirements of the database. So actually we have a lot of thinking about this part. So firstly, we're thinking about some relational database like MySQL. However, we find that a relational database can be challenging choice because of the scalability. So you can imagine that the load of location updates from taxi, and because the relational database has a high requirements on transaction, so it will lock up the database because of deletion. However, if we don't delete the old locations, we will end up paying the price in selection. Besides, we will need index to speed up the queries we mentioned in the design. Either approach will hurt the performance of index, and we end up further locking up the database. At the end, our system won't be able to keep up with the location updates, and API will start serving stellar data to customers. We also think about MongoDB. However, MongoDB cannot meet our requirements too on the speed. So at last we decide to choose Redis. Redis is an in-memory database which can meet our requirements for speed and high read-write throughput.
As we mentioned before, one major function for backend part is searching, and one important concept here is called geohash. Geohash is an alphanumeric string expressing a latitude-longitude location. It converts 2D value to 1D value. A geohash identifies a rectangular area. The longer geohash length is, the smaller rectangular area it can represent. And geohash is efficient in searching. Searching potential passengers for a driver is actually finding all passengers with same geohash ID with that driver. So here is the overview for our backend part. The left side is a flowchart showing how backend side manipulates each request. It looks a bit complex, but actually it just contains two main steps: information updating and user searching. The right side shows our three Redis database, and database 0, database 1 are used to synchronize the real-time information with users. Database 2 is used for searching. As you can see, here we use geohash code as key, and the value part stores all the user IDs in that geohash area.
Okay, then let's talk about our front end of the taxi application. Actually, we use React and Redux to build the front end system. As you can see the left, so the user can input their locations, and the web page will send a request to our backend and get all the locations surrounding drivers, and it will be sent back to the web page, and the web page will parse the locations in the map. Actually, here we use Google Map API. Actually, this GIF is from our demo. It's kind of a stress test to our system. As you can see, the number of locations of drivers increased dramatically, and all of this will be visualized in our this front end platform.
Okay, so now we'll talk about the benchmark parts of our project. So in this project, we not only develop this whole taxi applications which enables people to go and search passengers or drivers around them. We also want to use this application as a benchmark tools to have us get deeper understanding of the OpenWhisk or of the whole function as service platforms. Firstly, how to evaluate the performance of our application running on the OpenWhisk. We decide to evaluate the average latency from a user perspective, both when the load is low or when the load is high. Secondly, we want to evaluate the computational elasticity of OpenWhisk, how the auto balance sequence works and when the load changes rapidly. To accomplish this, we analyze two different scenarios: when there is only one OpenWhisk node or when there are two or more nodes. So in this project, we implement a matrix dashboard. It helps us take a look at the current status of OpenWhisk nodes in the Kubernetes clusters, like the CPU usage, the number of actions executed, or the number of containers created. Also, in order to rapidly change the load of OpenWhisk and analyze the computational elasticity, we developed a monitoring program. This program directly interacts with the API endpoints and will monitor the great number of drivers requesting the API. So here's a quick summary of how we gather all the metrics needed. OpenWhisk actually supports outputting metrics. All we need to do is enable it in the configurations. In order to gather all the metrics data and reorganize it with time series, we use Prometheus to scrape and store the metrics data every several seconds. To show the metrics, we use the visualization tool Grafana and design a metrics dashboard. For the simulation part, we also made some simulation programs to better evaluate our benchmark. We firstly made a Java program simulates users requesting to try to stress the service. Also, we made a Python program to test real-time server latency by just sending the simple request.
Here's one example of our demo showing the monitoring of the benchmarks. Below here you can see the latency we test. The latency test by running a simple Java program sending requests to the OpenWhisk. We just measure the time of the sending the request and receiving the response from OpenWhisk to be the latency for our OpenWhisk system. Above here you see is counting the invoker activation start for the two invokers, which you can just understand as the workload for the two invokers. What we want to see on the OpenWhisk is that two works are evenly distributed on two invokers, and the works are kind of like every invoker has some job to do. And you can see here on here you can see which are monitoring. First, one program starts and the yellow line rises up, means that the first invoker has some job to do. And then the green line rises up, showing that when the second program runs, the workload is shared to the second invoker. And we can see that for OpenWhisk, it can really distribute work on the two invokers. And for the analysis for the invoker number 1 versus 2, we've run some program on one invoker versus on two invokers. We see that for the single invoker, the average latency changes dramatically for the run before the program run and during the program run. That is, when we are running something using our taxi driver and passenger program, the latency for a simple Java program goes up to about 4,000 milliseconds. But when we are using the double invokers, the average latency actually remains unchanged. That is, two invokers can actually really well handle all the requests during this period and can really do a good job. So we can do more we can learn more from this graph from our latency test. First, we can see that two programs share two invokers. We can see when they start and when they end. And one thing is really interesting in this is that you can see that base level, there's a small program running on here, and which is the latency test level. What is more interesting is that when nothing's on, the latency test is on invoker 1, and when program is running on invoker 1, the latency test program is automatically migrated to program 2, and which shows that OpenWhisk actually can change the running invoker for the simple program during the running. And then when program 1 ends, the latency test program is automatically goes back to the invoker 1. This base level for the latency test shows really good property of OpenWhisk. And we have more stories to tell about this thing. Besides all the previous things, successful analysis and the successful tries showing the properties of OpenWhisk, we also have some problems. But the problems, we think they are really useful for us to study about OpenWhisk. So first thing, the sharing load thing happened only to different functions, which means that if we only run one function, calling one function, sending requests for the same question, the invokers will they will only run on one invoker and will never run on the second invoker, which is we found it's really strange, and we have some possible explanations for that, but we're not sure for that. First possible explanation is that OpenWhisk is run limited to functions. Each function has a special function ID in OpenWhisk, and calling the same function ID in OpenWhisk will not cause will not let the OpenWhisk to distribute it on two invokers. Second possible reason is that maybe our Java program running calling the drivers, passengers, calling requests still not yet reached the limit for OpenWhisk. Either way, we're not so far. By the end of this semester, we're still not quite sure about the answer for this one, but we still think this is a really interesting problem to study at. So we just record it here and hope that this is so far what we learned from this. So for the result for matrix analysis, we showed that we observed that OpenWhisk can distribute workload on different invokers, and we also found that during our trials, OpenWhisk have issues trying to distribute work for exactly the same function, but it can distribute it for different functions. So last part is the semester review. For this is a really it's been a long and rewarding semester, and we learned a lot from this, learn a lot from the course, from our mentors, and from our successful results, and from all our failures. So this part is kind of like we want to do a review for what we've done, what we've been through in this semester, and about like what we learned in this project. So I'll just start with our struggling history. Yeah. So yeah, nothing is really easy in this procedure. Like I still remember when the first really hard point we did is to deploy the OpenWhisk. We spent about 2 weeks deploying the OpenWhisk on Mac and on Linux, and we failed on Windows virtual machines, and eventually we gave up the Windows one. And also the same thing happened again later on when we tried to deploy the GCP. And I still remember the panic like of having nothing to present before our first sprint demo. Also, we learned like when we start to use OpenWhisk, we need to try to learn how to deploy OpenWhisk actions, how to make requests, how to communicate with OpenWhisk. Also, when we designed the taxi driver passenger system, we made huge amount of discussion with our mentors, and they gave us really good guidance, and they gave us some directions to do, like how should we tackle this problem, what kind of thing we need, what kind of things are the things we need, and how we should design our functions. And then after that, we'll just do discussions and gradually add and delete lots of functions, and we even change our language, from Python to Java once. So it's a long journey but rewarding one. And also for the matrix, actually similar thing just happened again. We just struggled to begin the monitoring, and cannot get the first metric from the beginning, and also we need to change the OpenWhisk log file, and also things just go down, and redeploy the OpenWhisk on Kubernetes on GCP again and again, and also sending a request, program will fail, everything will fail, and we just redo it. And also, but each time we just learn from it. But I must say that through all these failure things, I think teamwork is the one that has been successful all through here, and we had a great team, and each team member is contributing great to this project, and we feel really feel that we're in a great team and doing some really good teamwork here, and we learn how agile works and how we can build a project, and also we and we have really great guidance from our mentors. So for all those struggling histories, what we want to say is that we learn a lot from all of these. From the weeks we deploy on OpenWhisk locally and globally, we learn like cloud computing related skills, OpenWhisk, Minikube, Kubernetes, and GCP. From learning how to use OpenWhisk, build Whisk actions, we learn lots of knowledge in OpenWhisk with no knowledge in web development. From the designing taxi passenger driver system, we learn system design, OOD, we learn database, Redis, and we know Python and Java development skills. From the struggling to get our metrics out, we know Grafana, we learn latency test, and we know OpenWhisk metrics, and we know a lot more. And also meeting with our mentors, gathering every now and then, fighting for the sprint demos, which is no teamwork and strengthen other skills and work in an agile team. And also we learn lots of experience and stories from our mentors. So yeah, that's pretty much about it. This is the end of our presentation, and just a really brief summary of what we've done for the semester. And we've successfully deployed OpenWhisk on Minikube locally, Kubernetes and GCP. We made an application for driver passenger system, and then we built a benchmarking method for OpenWhisk running our application. That's about all the things we've done here. And in the end, we really want to express our thanks to our mentors Tom and Lam, also to Professor Krieger and all the instructors in this course. We found that we really learned a lot from this course, and we love this course. Yeah, thank you.